This video is on complex numbers, and the objectives are to use the imaginary unit I to write complex numbers, add, subtract, and multiply complex numbers. Use complex conjugates to write the quotient of two complex numbers in standard form. Find complex solutions to quadratic equations. Consider the quadratic equation x squared plus 1 equals 0. Now we see that we can't factor x squared plus 1 equals 0 because this is a sum of squares. A sum of squares is not factorable. If it was a difference of squares, it would be. So in order to solve for x, we will first try subtracting 1 from both sides. If we subtract 1, we get x squared equals negative 1. Now, in order to get rid of the second power here, we need to do the inverse of squaring, which is the square root. So it says, until now, you have always been told that you can't take the square root of a negative number. However, there is a term for the square root of negative numbers. So we take the square root of x squared and the square root of negative 1, we get x equals the square root of negative 1. That is known as a complex number. So we make the following definition, I. So we call the square root of negative 1 I. I equals the square root of negative 1. Note that squaring both sides would yield. If I squared both sides, I squared would equal negative 1. So these are two definitions that you need to definitely know. You need to definitely know that I equals the square root of negative 1, and you need to know that I squared equals negative 1. So memorize those definitions. Alright, here is basically an illustration of what complex numbers are in terms of real numbers and imaginary numbers. So it says real numbers and imaginary numbers are subsets of the set of complex numbers. So, just imagine complex numbers is the universe, and real could be Earth, right? And imaginary numbers could be Pluto. So these are all called complex numbers. But what we've been used to dealing with are real numbers, and now we're on the other planet of imaginary numbers. Pattern recognition. So let's say I equals I, of course, or square root of negative 1, and I squared equals negative 1. So I equals I, which is the square root of negative 1, and I squared equals negative 1. Then, what is I cubed? Well, if we know that, so write this down. I cubed is the same thing as I squared times I can split it up like that because I know what these two things are, because we already have the definitions, right? So I know that I squared equals negative 1, and I know that I equals I. So I cubed equals negative I, or negative square root of negative 1. But this looks better. Alright, if I wanted to split up I to the 4th, you could split it up however you want, but since I know what I squared is, I'm going to multiply I squared times I squared. So I to the 4th, since I know I squared equals negative 1 times a negative 1, I to the 4th must equal positive 1. Alright, I to the 5th. How do you want to split it up? It doesn't matter. You can split it up as I to the 4th times I, or I cubed times I squared. However you want to do it. Let's do I to the 4th times I, since I know that I to the 4th equals 1. So 1 times I, so I to the 5th equals I again. Alright, I to the 6th. You can split it up in so many different ways. You can even split it up as I squared times I squared times I squared, because Hey, that's I to the 6th. I know that I squared equals negative 1 times another negative 1 times another negative 1. So I to the 6th equals negative 1. Alright, so notice the pattern here. I equals I squared equals negative 1, I cubed equals negative I to the 4th equals 1, I to the 5th equals I to the 6th equals negative 1. Is there a pattern here? Well, it looks like this is cyclical. CYCLICAL, because we start with I, negative 1, negative I, 1. Then notice we start again. I, negative 1. So I know that I to the 7th would be negative I to the 8th would be 1. And then it'll just start all the way back over in a pattern. Alright, the next thing, let's talk about the definition of a complex number. A complex number is a combination of a real number and an imaginary number. So an example would be in this form, a plus bi, where a is the real part, so that's normally just a regular number, and the b is considered to be the imaginary part because it is multiplied times the I. Alright, so we have two parts, real part and imaginary part, and of course I equals the square root of negative 1. Here are some examples. For example, 1 plus I, a would be 1, b would be 1. 39 plus 3i, a would be 39, b would be 3. A would be 0.8 here, b would be negative 2.2. A would be negative 2, b would be pi. A would be the square root of 2, and here b would be 1 over 2. Alright, so a complex number has a real part and an imaginary part, but either part can be 0, so all real numbers and imaginary numbers are also complex numbers. So here, this is just a table breaking down what's the real part of this complex number, 3. What's the imaginary part, 2. What's the real part of 5, 5. There's no imaginary part, so we say 0. Here, there's no real part of negative 6i, so it's 0, and the imaginary part is negative 6. Alright, now let's add and subtract complex numbers. This actually works the same way as adding like terms, so I'm not going to treat it differently. Alright, so if we have 6 minus 4i plus 1 plus 3i, in this table here, as you can see, they explain it that you put the real parts together and you put the imaginary parts together. So really, the easiest way to think of it is adding like terms. So here, let's write it out. This would be 6 minus 4i plus 1 plus 3i. The like terms, we have 6 plus 1, and then we have negative 4i plus 3i. So the answer would just be 7, because 6 plus 1 is 7. And negative 4i plus 3i is negative I. So the answer is 7 minus I. Alright, next, let's go to B. Here we have subtraction. So what should you be careful about here? And when I give students tests on this section, someone always seems to not distribute the negative. Even though I emphasize it over and over again, someone still try to subtract this without distributing the negative. So I would take that extra step to write everything down. 3 minus 2i, and let's distribute negative 5, and then we have a positive 4i. So the like terms are 3 minus 5, which is negative 2, and we have negative 2i plus 4i, which is 2i. So the answer is negative 2 plus 2i. Moving on, let's do another one. 3 plus 2i minus 6. So let's distribute. Minus 13i. Our like terms are 3 minus 6 and 2i minus 13i. So the answer is negative 3, since 3 minus 6 is negative 3, and 2i minus 13i is negative 11i. So negative 3 minus 11i is the answer. So hopefully by now you understand that that's very easy, similar to adding like terms. Now let's move on to multiplying complex numbers. So here is a illustration of how you multiply. Notice it's the same thing as FOILing, because we are multiplying 2 terms times 2 terms. So we're going to do the same thing as with regular numbers. We're going to FOIL. 6 times 2, 12. 6 times negative 3i, negative 18i. Negative 2i times 2, negative 4i. And negative 2i times negative 3i is a positive 6i squared. So here's where we get into something that's new to you. Alright, because we know that I squared equals what? Do you recall what I squared equals from the first page? So go back to the first page where I can go back to show you. So it looks like I squared equals negative 1. So again, memorize these two equations. I squared equals negative 1. So I know I can do a substitution at some point. So let's go ahead and work on what we know. We know that we have 12 minus, here we have negative 22i plus 6 times negative 1, because I squared is the same thing as negative 1. Now we have 12 minus 22i minus 6, which simplifies to 6 minus 22i, since 12 minus 6 is 6. 6 minus 22i is our answer. And notice I try to write the real part first and the imaginary part second, just because that's how it was written up here. So notice they wrote the real part and then the imaginary part. So try to use that convention. Alright, next we're going to work on E. E is 3 plus 2i times 3 minus 2i. Now that should look familiar to you from Math 100, because isn't it similar to a difference of squares? So I know something will cancel just because we have the same terms here, but the signs are different in the middle. 3 times 3, 9. 3 times negative 2i, negative 6i. 2i times 3, positive 6i. 2i times negative 2i, negative 4i squared. So that's 9. This cancels. Minus 4 times I squared is a negative 1. Alright, so now we have 9 plus 4, which equals 13. Thirteen is the answer. So notice that when we multiply conjugates, so these are called conjugates, which we will talk about in the next section. Conjugates are when you have the same numbers but the signs are different in the middle. So notice that when we multiply conjugates together, we don't get an imaginary part anymore. We just get a real part. So this information is useful for the next topic. Alright, let's talk about complex conjugates, a pair of complex numbers of the form a plus bi and a minus bi, where a and b are real numbers. So again, this is the form of conjugates. So they look the same, a and bi are the same, but there's a plus sign in the middle of those two terms and a minus sign in the middle of those two terms, then they are conjugates. Alright, a conjugate is where we change the sign in the middle like this. So another image to help you understand what a conjugate is. Now it says simplify. 3i over 2 plus 4i. So it turns out, just like radicals, we can't have i's in the denominator. So again, we have to get this I out of the denominator. So get the I out of the denominator. And how can we do this? Well, you can just multiply numerator and denominator by the conjugate of 2 plus 4i, because when we multiply conjugates together, notice that we get a plain real number, no imaginary part, therefore no I. So first of all, figure out what is the conjugate of 2 plus 4i. So the conjugate is 2 minus 4i. So whatever you decide the conjugate is here, you keep it. You have to write the same thing here. So that would be 3i times 2, 6i. 3i times negative 4i, negative 12i squared. We'll come back for that. And in the bottom, we should already know that the middles will cancel out. 2 times 2, 4. So I'm not even going to go through the middle, but you can. Let's go through it. 2 times negative 4i, negative 8i. 4i times 2, positive 8i. And 4i times negative 4i is negative 16i squared. Alright, again, that cancels here, which it should. It always should, because we're multiplying conjugates times each other. Alright, now in the numerator we have a 6i minus 12. We can make a substitution here because I squared equals negative 1. Then we have 4 minus 16 times another negative 1 because of that I squared there. So we have 6i plus 12 over 4 plus 16 right now, which is 6i plus 12 over 20. Now, obviously we can reduce this, and I'm even going to split it up so that there are two terms, a term and the bi term. So here we go. Alright, move it over here. I know it's going to be 6i over 20, and it's going to be a 12 over 20 because everything in the numerator is being divided by 20. So I can split it up this way, and then I can reduce each term separately. 2 can go into 6 3 times. 2 can go in 20 10 times. Alright, 4 can go in 12 3 times. 4 can go into 20 5 times. Alright, so since this is the real part, I will write 3/5 first, then I will write 3/10 over 3/10 I. So I'm just writing the real part first and then the imaginary part. Alright, I think I skipped something over here to the right. I said multiply each number by complex conjugate, but I'm going to skip that because I've already emphasized that when you multiply by the conjugate, then you'll get a real number. So you can do that on your own. Alright, next we have square roots of negative numbers. So it turns out that -2 times -3 equals I times square root of 2 times I times the square root of 3. So where did that come from? Well, the square root of -r equals I times the square root of r. Because here, square root of -r is the same thing as the square root of -1 times r. Right? And since we can split this up, there's a rule that says we can split this up as the square root of -1 times the square root of r. And guess what? We should know that by now that the square root of -1 is I. So I times the square root of r. So anytime we have a negative under our radical, we have to pull it out. Alright, so A, very easy. Just a reminder that I equals the square root of -1. Here we have the square root. I do a little bit more work because we know that it's -1 times 16. So we need to separate that -1 so that we can get the I out of the radical. We can split this up as the square root of -1 times the square root of 16, which is I times 4, because the square root of 16 is 4. So the answer is just 4i. No real part there. Alright, the square root of -3. How can you split up that number? Well, -1 times 3, of course. Then that can split up as the square root of -1 times the square root of 3. This time, 3 is not a perfect square. So we have I times the square root of 3. Or, you may see this in Weber's line, that is square root of 3 times I. But please, don't mistake, that I is not under the radical, right? So that's why I prefer writing it this way, I radical 3, instead of the square root of 3i, because sometimes you make a mistake and put that I under the radical, and that's not the same. So make sure you space between square root of 3 and I. Alright, next we have the square root of -8, which is -1 times 4 times 2. We got to get that perfect square out. So that's why I had to break down 8. Alright, so that's the square root of -1 times the square root of 4 times the square root of 2. I know that square root of -1 is I, square root of 4 is 2, and of course 2 is not a perfect square, so it stays under the radical. So the answer here is 2i square root of 2. So I just pull that 2 in the front. Alright, so 2i radical 2. Alright, next we're going to write the complex number in standard form. Alright, write the complex. Now I did have a note over here that if you have square root of -2 times square root of -3, you have to pull out the I first. Okay, you can't multiply -2 times -3 and get the square root of 6. You have to pull out the i's first. So square root of -2 is I square root of 2. Square root of -3 is I square root of 3, because we had to pull out the square root of -1. Then you multiply I times I. I times I is I squared. Square root of 2 square root of 3 is square root of 6. So the answer is negative square root of 6 since I squared is negative 1. So you cannot just go ahead and multiply this out, because notice you're not going to get the same answer. With complex numbers, you have to pull out the I first. Alright, write the complex number in standard form. Alright, we want to write it as a plus bi. So here we have 1 plus, and guess what? We did this already. We already did square root of negative 8. So we know that it's going to be 2i square root of 2. So to write it in standard form, write it as the a plus bi format. So that's why I wrote my real part first, which is 1, and my imaginary part second, which is really 2 radical 2. Alright, here again, we have to pull out. So I know that's, and we actually did this one, I think. Well, maybe not. Negative 1 times square root of 6 times negative 1 times square root of 2. So square root of negative 1 is I square root of 6. Square root of negative 1 again, I square root of 2. So we have I squared square root of 12. Now notice, this is an interesting problem because although 6 and 12 were not perfect squares and did not contain perfect squares, when we multiplied 6 and 12 together, it became a product that contained a perfect square factor. So we have to get that 4 out. So 4 times 3 here. Square root of 4 is 2. I squared is negative 1. So our final answer is negative 2 times the square root of 3. Alright, last we have something called complex solutions of a quadratic equation. So we have two problems. X squared plus 4 equals 0, 3x squared minus 2x plus 5 equals 0. So how many solutions should we have if we have a quadratic equation? Two solutions. Alright, so let's look at x squared plus 4 equals 0. We know that x squared equals negative 4. Now what is the missing step here? So how do I get from this to this? How do I get rid of that squared symbol? Well, you need to find the square root of both sides. Alright, so square root of x squared will give you that x, right? But here, of course, you got to split that up as negative 1 times 4, which is I times 2. Alright, but anytime you're doing this, you're really supposed to put that plus minus symbol there, so that you'll know there are two answers because our degree is 2. So that's why the complex solutions are positive 2i and negative 2i. Let's go with 3x squared minus 2x plus 5. Now normally we try to factor this. So 3 times 5 is 15. Are there factors of 15 that give you negative 2? Let's try it. 5 and 3. It's not going to work because I need to multiply two numbers to get positive 15, and this gives me a negative 15. So of course, if you can't factor a quadratic equation, what must you do? You must use the quadratic formula. So the quadratic formula is, say it with me, x equals negative c plus or minus square root b squared minus 4ac all over 2a, where a equals what in this case? A equals 3, b equals negative 2, and c equals 5. So let's plug that into our quadratic equation. I'll get x equals negative 2 plus or minus square root negative 2 squared minus 4 times 3 times 5 all over 2 times 3, which is x equals positive 2 plus or minus square root 4 minus, what is 12 times 5? 60 over 6. X equals negative, well, positive 2 plus or minus square root negative 56 over 6, because 4 minus 60 is negative 56. Now, you need to determine whether or not 56 contains a perfect square. Alright, and it does. It contains 4. Alright, it contains 4, so x equals 2 plus or minus square root. I have a negative 1 in there, I got a 4, I got a 14, divided by 6. So that's 2 plus or minus square root. Well, let's take out the I. Since square root of negative 1 is I, and the square root of 4 is 2, let's take out 2I square root of 14 over 6. Now, when all three numbers are divisible by a number, you need to simplify. All three of these numbers on the outside, of course. You can't touch that number under the radical. Alright, it's sort of like in jail. You can't get to it, okay? So, only the numbers on the outside. Alright? So, 2 can go into all of these numbers. 2 goes in 2 one time. 2 goes in that 2 one time. 1 times I is still I. Square root of 14. 2 goes into 6 3 times. So the answer is 1 plus or minus I times the square root of 14 over 3. So your two solutions are, and let me write it out. Let's call the first solution x of 1. It would be 1 plus I times the square root of 14 over 3. And x of 2 would be 1 minus I times the square root of 14 over 3. So those are your solutions. And that's basically a tutorial of complex numbers in a short time. Hopefully you get some understanding from it. And let me know if you have any questions.